Have you ever wondered what lies at the heart of everything around us? Your pen, your notebook, even you and me. Science tells us that all matter is made up of atoms. But how did we first come to know about this mysterious building block of matter? That is what we will explore today. Thousands of years ago, before we had microscopes or experiments, early Indian philosophers and Greek thinkers, they already asked this big question: what is matter made of? They believed that matter is built from fundamental building blocks, something so small that it cannot be divided further. Isn't it fascinating that even in BC times, they were already imagining the existence of atoms? Now let's talk about atom. The word atom comes from the Greek word atomio, which means uncuttable or indivisible. Philosophers, they thought that once you reach the atom, you cannot cut it any further. It's the final piece of that matter. Of course, today we know there is much more to that story. But this idea was the seed for everything that followed. Now let's jump to 1808. A British school teacher, John Dalton, gave us the first scientific theory of atom. His theory explained matter in a systematic way. He said, matter is made up of tiny individual particles called atoms. Atoms combine in fixed ratio to form compounds. And they follow certain laws, like the law of conservation of mass, law of constant composition, and law of multiple proportions. Dalton's theory was revolutionary. It gave science a framework to explain chemical reactions. But Dalton wasn't entirely right. His model failed to explain electricity. For example, why rubbing glass with silk or fur produces charges. It also couldn't explain subatomic discoveries that came later. This shows us something important in science. Every theory is a stepping stone. It explains some part, but leaves the question for the future. And that brings us to the exciting next step, the discovery of electrons, protons, and neutrons. These discoveries completely changed our understanding of the atom, and we'll explore them in upcoming modules. Before we move on to the next part, let me introduce you to the Research Goal platform. At Research Goal, you will find research-driven courses that offer real research skills, data analysis training, and publication support. And best of all, it is incredibly affordable, costing less than other platforms. Join Research Goal today for free. Check out the link in the description box. The discovery of electron was one of the most important milestones in the modern science. Until the mid-19th century, atoms were believed to be indivisible. But careful experiments on electricity and matter gradually revealed the existence of universally negatively charged particles, the electrons. Let's carefully trace how this discovery was made. In 1830, Michael Faraday demonstrated that when electricity passes through electrolytes, chemical changes occur at the electrodes, leading to the deposition of matter. This suggested that electricity is not just continuous, but it may be carried by discrete particles associated with atoms. This idea laid the foundation of later work on the particulate nature of electricity. By the mid-19th century, scientists turned to gases. They used glass tubes, partially evacuated with vacuum pump, and fitted with two electrodes, cathode, which is negatively charged, and anode, which is positively charged. At ordinary pressure, no conduction was absorbed. But at low pressure and under very high voltage, a strange phenomena occurred. A stream seems to be emerged from the cathode and move towards the anode. These invisible rays later were called cathode rays. To test whether these rays were just light or actual particles, scientists modified the discharge tube. They made the anode perforated and coated with the glass behind it with zinc sulfide. When cathode rays passed through the hole and struck the coating, a bright fluorescent spot appeared. This clearly showed cathode rays consist of material particles, not just light waves. These particles carried momentum and could produce mechanical effects. Detailed experiments revealed some of the important properties of cathode rays. Cathode rays originate at cathode and move in a straight line towards anode. They are invisible to human eye. They are deflected by electric and magnetic fields. They produce mechanical effects. They are independent of gas and electrode material. From these, the conclusion was straightforward. Cathode rays are streams of fundamental negatively charged particles, which later came to be called electrons. Well, this was revolutionary. It proved for the first time atoms contain smaller subatomic particles, the electrons. They were discovered through cathode ray experiments, become the first subatomic particle known to science. opening the path of Thomson's experiments, the charge to mass ratio determination, and eventually the complete structure of the atom. The discovery of electron was not accidental. It was the result of systematic experimentation, careful observation, as well as logical reasoning. For your CSIR-UGC exam, remember both the scientific or the experimental setup, which is discharge tube, low pressure, high voltage, fluorescent coating, and etc., and also the conceptual understanding. For example, where the negative charge, where the positive charge is, what is particle nature, etc. These fundamental discoveries, they reshaped the atomic theory, leading to the modern era of physics and chemistry. That is why this topic is very, very important. We'll cover some of the MCQs, but let's first clear the basic concepts in detail. In 1897, British physicist J.J. Thomson made a landmark contribution to atomic physics by determining the charge to mass ratio of the electron. This experiment not only revealed important information about the fundamental particle of matter, which is the electron, but also laid the foundation for modern subatomic physics. Thomson used a cathode ray tube, CRT, and applied both an electric field and a magnetic field, oriented perpendicular to each other and to the path of cathode rays. The CRT, which is cathode ray tube, allowed him to observe the path of electron beam under different conditions. Case 1. When only the electric field was applied. When only the electric field was applied, the negatively charged electrons were deflected towards the positively charged plate. On the fluorescent screen, this reflection was visible at a point A. When only the magnetic field was applied, the force due to magnetic interaction caused deflection in the opposite direction. The electron struck the screen at point C. By carefully adjusting the strength of both electric and magnetic fields, Thomson was able to balance these two forces. Under the balance, the electron beam traveled undeflected, striking the screen at point B, which is the same position as if no field was present. This balancing allowed precise calculation of charge to mass ratio. Thomson reasoned that the deviation of the electron depends on two key factors. Factor number 1, charge of the particle E. A greater negative charge increases the interaction with the fields, producing larger deflections. The second one is the mass of the particle. A lighter particle experiences greater acceleration under the same force, hence larger deflection. Thus, the observed deflections could be mathematically related to the ratio E upon m. Later, the accurate measurements were done, and it was found out that E upon m is equals to 1.758820 multiplied by 10 to the power 11 coulombs per kg, where me is the mass of the electron in kilograms and E is the magnitude of the charge on the electron in coulomb. Next is a calculation of the charge on the electron. R.A. Millikan, he did the experiment called oil drop method in 1906 to 1914, where he was able to calculate the charge of the electron. So when he calculated the charge of the electron, it turned out to be minus 1.6 multiplied by 10 to the power minus 19 coulomb. And today, what exactly is the charge of the electron, which is minus 1.602176 multiplied by 10 to the power 19 coulomb. Very, very close to the value he calculated. Using these values, we can easily calculate the mass of the electron from this equation, which is E upon me is equals to 1.602176 multiplied by 10 to the power 19 coulomb and 1.758820 multiplied by 10 to the power 11 coulomb per kg. And if we solve this, the value is exactly 9.1094 multiplied by 10 to the power minus 31 kilograms. And this is the mass of the electron.